Hello and welcome back to Manifolds, the video series where we talk a lot about generalized surfaces and how we can do integration on them. In fact, we almost reached the point that we can tell how to integrate so-called volume forms. However, before we do that, we first look at some examples in today's part 36. Indeed, we already know that for orientable Riemannian manifolds, we have so-called canonical volume forms. But before we start with the examples for these, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via Patreon. And please don't forget, with the link in the description, you can download additional materials for the videos. Okay, then let's immediately start with the assumption here. M should be an orientable Riemannian manifold. And the corresponding dimension we simply fix as n. Now, there we consider volume forms, and we already know these are n-forms. In particular, we have shown that we have exactly one canonical volume form. And we denote this by omega m, and we know it has a very nice local representation. Namely, if we have a chart H and a parameterization phi, then the determinant of Gram comes in. More precisely, we have the square root of the determinant of this G matrix, and then we have the standard dual basis. Okay, so this is the canonical volume form in local coordinates, and it's important to remember because when we do the integration on manifolds, this will be the standard form we integrate. And this is the reason for looking at examples in this video. And in fact, in part 34, we already saw one example, so let's quickly recall that one. It was given by the common two-dimensional sphere with a standard parameterization. So we have the so-called spherical coordinates, and they are denoted by capital phi. Simply because the lowercase phi is already used as an angle there. Indeed, what you should remember here is that we need only two angles to characterize a point on the sphere. And the angle theta here is measured from the North Pole. And on the other hand, phi is measured as the angle on the equator plane here. So it's not so complicated, but it's still important to remember how this formula looks like. And then what we get, simply by calculating partial derivatives, is this matrix G on the sphere. So you see, we already assumed that S2 is a Riemannian manifold with the standard inner product on it. But then the restriction of this inner product to the sphere gives us this matrix G. And therefore, we also get our canonical volume form immediately. And this is something you might also already know. We have the sine of theta in the volume form. Sine of theta here is always a positive number because we go through the inputs 0 to pi. Hence, we don't need to write an absolute value here. Okay, there we have it. This is our canonical volume form here, and you might already know that from standard integrations in spherical coordinates. However, now you also know this is just a general outcome by considering Riemannian manifolds. Okay, then let's go to the next example, which we can also fix as a two-dimensional one. Namely, I want to look at a graph surface. Hence, this can be generalized to higher dimensional examples, but let's start with a two-dimensional here. So let's consider a nice function f from R2 to R, and let's say it's a C infinity function. Hence, we can visualize the graph of this function in the three-dimensional space. So what we get is a two-dimensional graph surface. And you also know that charts are not a problem for that because we already have the map from the domain to the surface. So let's say we have a U tilde here in R2, and then we can simply use our map F to get our manifold embedded in R3. So essentially everything here is really simple. We can write M as a pair, where we have the coordinate x and the value f of x. And that's it, and we can just go through all possible inputs x. So we could say we go through all x in R2, or we restrict it to an open domain U tilde. This is not so important because in the end we are interested in the local behavior anyway. But clearly what we get here is a two-dimensional submanifold in R3. Hence, we already have a standard Riemannian metric on it. And now the question is, what does it mean for our canonical volume form for this manifold? Of course, we can just use the parameterization we already talked about. So we have phi that takes a point x here from R2 and sends it to the surface. So not complicated at all, we just use the map f. And since we have a well-defined function f, we can also just go back. Hence for the chart h, we just project back. Okay, and then we can just calculate tangent vectors, namely we calculate the coordinate basis of the tangent space. And as common for submanifolds, we can identify the tangent space with the tangent space for submanifolds. In other words, the tangent vector can just be written as a partial derivative of phi. Namely, the first one has to be with respect to the first coordinate in R2. And of course, we also have the identification with the point x in U tilde and the point P on the manifold. So not a big problem, but now the question is, what is the derivative of phi? Now since this pair here represents three components, x1, x2 and f of x, we have a vector in R3. And the derivative just gives us 1, 0 and the partial derivative of f. So we just write df dx1. And of course, this is also evaluated at the point x. So not so complicated, this is our first tangent vector. And the second one is already the last one, and we just have to change 1 to 2. And then we just get a vector which is 0, 1 partial derivative of f again. And obviously here the partial derivative with respect to x2. And that's it. And there you can already see, generalizing that to an n-dimensional graph surface is not complicated at all. You just have n tangent vectors where you shift the 1 through the vector. Okay, the next step would be calculating the Riemannian metric on M, or more precisely, calculating the matrix G. And please recall, in general for submanifolds we put in the tangent vectors, which means we put in the partial derivatives of phi. And then, in this case here, we just have the standard inner product in R3. And here we can conclude that we get two different cases. Namely, if I and j are not equal, we have the inner product of these two vectors here. This means only the last component here remains. So in general, we just have df dxi times df dxj. So this is the first case, so the indices are not the same, and the second case is for I is equal to j. There we just have one component with 1 and the last component as well. So we have 1 plus the same thing as before, but actually we have a square here. Okay, so this is our result that also holds for the n-dimensional case, but let's write it down for the 2-dimensional case as we had it here. This simply means that our G is a 2 times 2 matrix. On the diagonal we have 1 plus df dx1 squared and df dx2 squared. And then on the off diagonal we don't have the 1 in front, we just have df dx1 times df dx2. And of course we have the same entry here and there because it's just a product. Okay, I omitted the notation here, but you know everything depends on the point x here as well. Okay, but now for the canonical volume form, you know we need the determinant of G. And of course this is easy to calculate because we just have a 2 times 2 matrix. And also by multiplying and subtracting, some parts cancel out, so what remains is df dx1 squared plus the same thing with df dx2. So we get 1 plus the sum of the squares of the partial derivatives. And here I can also tell you, this nicely generalizes to the n-dimensional case as well. You just have a longer sum in this case. Okay, now we are finally ready to write down the canonical volume form for a graph surface. So essentially, we just have the square root of this determinant here. And as always on the right, we just have the standard volume form that comes from R2 here. So now you already know, if you want to integrate the canonical volume form for a graph surface, this factor here comes in. However, at least in our 2-dimensional case here, we have a very interesting fact. Namely, because the tangent vectors are vectors in R3, we can calculate the cross product. So this vector product of the two tangent vectors gives us again a vector in R3. So we can use the Euclidean norm in R3 to calculate the length of this vector. So here I would say we can just do it because it's not complicated at all. There are ones and zeros involved, so the computation is simple. In fact, we simply get the partial derivative in the first and second component. And I would say that there is a minus sign is not a big deal at all. We calculate the norm anyway, and now what we see is that we get the same result as before. So you see, we get the determinant of G with this calculation as well. Perhaps this is an interesting or surprising fact, but it just comes from the property of the cross product. In particular, you should know that the length of the cross product vector measures two-dimensional areas. So exactly what we want for the canonical volume form in 2 dimensions. However, I would say it's worth it to generalize this connection here even more because it's used very often. So we will do this in the next video, but after that we can finally start with integration. So I really hope we meet again and have a nice day. Bye bye.